Ground wires should not be interconnected between main switchboards, often referred to as MSB, of delta/Y transformers. When delta/Y transformers are connected in parallel, a critical consideration arises regarding the grounding system. The secondary neutral points of these transformers are deliberately kept separate and are not connected together. This isolation is crucial because the delta/Y configuration inherently lacks a direct path for neutral current to flow between the transformers. If the ground wires were to be interconnected, it would inadvertently create a parallel path for neutral current. This unintended path can lead to several problems within the transformer grounding system, potentially compromising its effectiveness and safety. The primary function of ground wires is to provide a low resistance path to ground for fault current. This low resistance path ensures that in the event of an electrical fault, such as a short circuit, the fault current can quickly and safely flow to ground, tripping circuit breakers or fuses and preventing electrical shock or equipment damage. Connecting the ground wires together would reduce the overall resistance to ground. While this might seem beneficial at first glance, it can actually increase the fault current. A higher fault current can exceed the interrupting capacity of protected devices, leading to equipment damage, arcing faults, and even fire hazards. Therefore, maintaining separate ground paths for each transformer is essential for ensuring the proper operation of the grounding system and the safety of the electrical system as a whole. Furthermore, each ground wire should be connected to its own dedicated ground rod or grounding electrode. This separation is crucial for achieving optimal grounding performance. Ground rods are typically made of copper or copper-clad steel and are driven deep into the earth to establish a connection to the earth's ground potential. The depth and number of ground rods required depend on local soil conditions and electrical codes. By connecting each ground wire to a separate ground rod, you ensure that each transformer has its own independent path to ground. This independence prevents circulating currents between the grounding systems of the two transformers and minimizes the risk of ground loops. Ground loops can introduce noise and interference into sensitive electronic equipment, as well as create hazardous touch potentials on grounded metal surfaces. The purpose of the ground wire is to provide a low resistance path to ground for fault current. This is achieved by connecting the ground wire to a grounding electrode, such as a ground rod or a metallic water pipe that is in direct contact with the earth for 10 feet or more. The grounding electrode provides a direct connection to the earth, allowing fault current to flow back to the source and trip the overcurrent protection device such as a circuit breaker or fuse. If the ground wires were connected together, it would reduce the overall resistance to ground, which could increase the fault current and the potential for equipment damage. This is because the fault current would have two paths to ground, which would effectively halve the resistance. A lower resistance means a high fault current, which could exceed the interrupting rating of the overcurrent protection device. The National Electrical Code, or NEC, provides specific requirements for grounding electrical systems. These requirements are designed to ensure that electrical systems are safely grounded and that fault current can be safely dissipated. It is important to consult the NEC and local electrical codes to ensure that all grounding requirements are met. NEC Section 250 covers grounding and bonding. It outlines the requirements for grounding electrical systems to ensure safety and proper operation. Some key aspects include grounding electrode systems, which specify the types of grounding electrodes that can be used, such as ground rods, metal water pipes, and concrete-encased electrodes. Grounding conductor sizing is also crucial, as it dictates the appropriate size of grounding conductors based on the size of the service entrance conductors. Bonding requirements ensure that all metal parts of an electrical system are properly bonded together to create a low impedance path for fault current. The NEC also addresses the grounding of specific equipment, such as transformers, generators, and motors. It is important to consult the latest edition of the NEC for the most up-to-date requirements. Now, let's talk more about delta/Y transformers. A delta/Y transformer is a type of three-phase transformer that has a delta-connected primary winding and a Y-connected secondary winding. The delta connection provides a stable voltage source, while the Y connection provides a neutral point that can be used for grounding. Delta/Y transformers are commonly used in power distribution systems to step down voltage from a high voltage transmission line to a low voltage distribution line. They are also used in industrial applications to provide power to three-phase equipment. The delta side of the transformer does not have a neutral connection, while the Y side does. The Y connection provides a neutral point that can be used for grounding. The neutral point is typically connected to a ground rod or other grounding electrode to provide a low resistance path to ground for fault current. When multiple delta/Y transformers are used in a system, it is important to ensure that the grounding systems are properly coordinated. This means that the neutral points of the transformers should not be connected together. Connecting the neutral points together can create a circulating current that can damage the transformers and other equipment. In addition, the ground wire should be connected to separate ground rods or grounding electrodes. This is to ensure that each transformer has its own independent path to ground. The size of the ground wire should be based on the size of the transformer windings. The NEC provides specific requirements for the size of ground wires. It is important to consult the NEC to ensure that the ground wires are properly sized. Let's also discuss about main switchboards. A main switchboard, or MSB, is a central distribution point for electrical power in a building or facility. It receives power from the utility company and distributes it to various loads throughout the building. The MSB typically contains circuit breakers, fuses, and other protective devices to protect the electrical system from overloads and short circuits. The MSB also contains metering equipment to measure the amount of power being consumed. The MSB is typically located in a dedicated electrical room. The electrical room should be well ventilated and kept free of moisture and debris. The MSB should be inspected regularly to ensure that it is in good working condition. Any damaged or worn component should be replaced immediately. When working on an MSB, it is important to follow all safety precautions. This includes wearing appropriate personal protective equipment, such as gloves and safety glasses. It is also important to de-energize the MSB before working on it. De-energizing the MSB involves turning off the main circuit breaker and verifying that there is no voltage present on any of the terminals. Here are some additional considerations for grounding delta/Y transformers. Firstly, the size of the grounding electrode conductor should be based on the size of the service entrance conductors, as specified in NEC Table 250.66. Secondly, the grounding electrode conductor should be connected to the grounding electrode using an approved method, such as a bolted connection or a compression connector. Thirdly, the grounding electrode should be located as close as practical to the transformer. Fourthly, if multiple grounding electrodes are used, they should be bonded together to form a grounding electrode system. Fifthly, the grounding electrode system should have a resistance to ground of 25 ohms or less, as measured by a ground resistance tester. Sixthly, the grounding system should be inspected regularly to ensure that it is in good working condition. Seventhly, any damaged or worn components should be replaced immediately. Eighthly, all electrical work should be performed by a qualified electrician who is familiar with the NEC and local electrical codes. Ninthly, proper documentation of the grounding system should be maintained, including records of inspections, testing, and repairs. Tenthly, ensure that all personnel working on or near the electrical system are properly trained in grounding procedures and safety practices. In summary, ground wires should not be interconnected between MSB of delta/Y transformers. Each transformer should have its own dedicated grounding system, including a separate ground rod or grounding electrode. This is to ensure that the grounding system functions properly and protects the electrical system from overloads and short circuits. Following these guidelines will help ensure the safety and reliability of the electrical system. Remember to always consult the NEC and local electrical codes for specific requirements. Grounding is a critical aspect of electrical safety and should not be taken lightly. Proper grounding protects equipment and personnel from electrical hazards.